Yes, students, let's continue with the second problem for today's class. This problem is all about the designing of an FIR band pass filter. If you could recollect the previous problems, we have designed a low pass filter, we have designed a high pass filter. Just similar to that, in today's class, let's just see how to design a given FIR band pass filter. Okay. They've just sort of sketched this response. This is the magnitude response for a given ideal band pass filter. This is the below sketch is the magnitude response for a given ideal band pass filter. Okay, so the band of frequencies is ranging between 1 radians to 2 radians. That is the value of the lower cutoff frequency omega c1 is 1 radians and the upper cutoff range is 2 radians. This is the plot given. Okay, and the problem statement goes like this: design an FIR band pass filter which is supposed to be having a duration of n is equal to 7. This HD of omega, capital HD of omega, is representing what? The ideal characteristic of the non-causal band pass filter. What we must notice, this is the characteristic of what? Of a non-causal band pass filter. I've repeated this n number of times in the earlier class. For a given filter to be causal in nature with respect to its impulse response, in the present context, if d of n is 0 for n less than 0, then it is causal in nature. Similarly, with respect, if you compare this in the frequency domain, the value of hg of omega should be 0 for n less than 0. But whereas in this case, there exists a spectrum even for value of omega less than 0. Hence, it is the case of a non-causal bandpass filter because the spectrum extends in the left hand axis also. So, the given response is the response of a non-causal ideal bandpass filter. What we are required to evaluate is to find the value of hd of n corresponding to hd of omega. That is point number 1. And in the second point, they have given the Hamming windowing function by this particular equation, and they're saying that this particular Hamming windowing function is said to be what? Ranging between minus of n minus 1 by 2 to plus n minus 1 by 2. So, what we are required to show at the end is that how the same windowing function, how the same windowing Hamming function can be used to design an FIR bandpass filter for the case what? For the case whose impulse response h of n, okay, is valid for small n lying between the range 0 to 6. Probably how is this equation different and how is this equation different? Okay, what exactly we are required to evaluate, we'll be able to understand it better as we proceed further in the problem solution. So let's get back to the solution. In solution, let's start. Let's begin with step number 1. Step number 1. So please note that in this case, okay, the equation for hg of omega has to be derived from the given characteristic. So let's solve in step number 1. Let's write it as from the given characteristic. Means what was the plotting given? From the given characteristic, we may say that what? The frequency response, the frequency response of ideal band pass filter is given by hd of omega is said to be equal to e to the power of minus j times alpha times omega for what? For what range? For omega c1 less than magnitude of omega less than omega c2 less than pi less than pi. Okay, or we just do one thing. We can just what write this only at in the range between omega c1 to omega c2 itself. It is 0. It is 0 otherwise. 0 otherwise. So only in the band between omega c1 to omega c2, the value is e to the power of minus j times alpha into omega. Outside this range, the value is 0. So what must find? Knowing hd of omega, we are required to find hd of n corresponding to subdivision A question. So what to find? We have to find the value of hd of omega. What is hd of omega? hd of hd of n. hd of n is the impulse response. Is the impulse response of an of a given ideal band pass filter. Hd of n is the impulse response of the ideal band pass filter. What is hd of omega? The concept, it is a frequency response of a given ideal band pass filter. So knowing hd of omega, the expression for hd of n goes like this. hd of n is equal to 1 divided by 2 pi times integral minus pi to plus pi h d of omega into e power j omega n d omega. The normal DTFT formula. Normal DTFT formula. Let's proceed further and substitute the appropriate limits. hd of n is nothing but equal to 1 divided by 2 pi, common factor. Now let us split the limits of integration as. What is the left hand side axis range? It varies from minus omega c2 to minus omega c1. The value is e to the power of minus j times alpha into omega multiplied by e power j omega n d omega. Towards the positive side, towards the RHS side, the range is from plus omega c1 to omega c2. The term within the integration symbol is e power minus j alpha omega into e power j omega n d omega. Close the square bracket. Close the square bracket. And now just try to bring the terms within the integration symbol under one single hat. So therefore, h d of n would be equal to 1 divided by 2 pi 2 pi integral minus omega c2 to minus omega c1. This is nothing but e power j times omega times n minus alpha d omega. Similarly, integral limits varying from omega c1 to omega c2 e to the power of j times omega times n minus alpha d omega. Now we can integrate it and substitute the appropriate limits. Okay. Therefore, h d of n is nothing but equal to 1 divided by 2 pi, the whole square bracket. Integration of this term is what? With the power of j times omega times n minus alpha. Since it is with respect to derivative omega, the coefficient is j times of n minus alpha. What are the limits? The limits are what? The limits are minus omega c1 and minus omega c2. Similarly, the second term, it's again e to the power of j times omega times n minus alpha. The coefficient is j times n minus alpha. The limits is omega c2 to omega c1. Close the square bracket. Close the square bracket. So once you could substitute, we end up in the equation as, therefore hd of n would be equal to 1 by 2 pi. For both the two terms, it is a common bracket, common denominator. So it is what? The first term is It's minus sign, is a minus sign, don't forget. Got e to the power of minus j times omega c1 of n minus alpha minus e to the power of minus j times of omega c2 of n minus alpha. Yes. Next, the second term, second set of terms, plus e to the power of j times of omega c2 of n minus alpha minus minus e to the power of j times omega c1 of n minus alpha n minus alpha. Yeah, common denominator, we forgot that completely. It is what? J times of n minus alpha. J times of n minus alpha. Please note that the common terms for omega c1 and omega c1. Okay, I'll combine the first term with the fourth term and combine the second term with the third term, applying Euler's formula for sine theta. Okay, e power j theta minus e power minus j theta would be equal to 2j sine theta. I'm employing the same formula over here. The things that where to search for the pointer. Yeah. Yes. No. Therefore, this will be hd of n. Hd of n will be equal to 1 by 2 pi j times n minus alpha. This is nothing but combining the first term with the fourth term, 2j times sine of omega c2 of n minus alpha minus 2j times this minus n, because it is e power c it is e power minus j minus e power j. Take care of this minus sign. This minus sign is coming into picture over here. Minus 2j times sine of omega c1 of n minus alpha. See, to take into account the second term, this e power j theta minus e power minus j theta, I got this term. Okay, the second and third term, for that I got this first term. By considering the first term and the fourth term, I'm getting the second term. So this, in both the first two terms, 2j is a common factor. By cancelling the 2j with this 2j, I end up in the equation for hd of n as 1 divided by pi times of n minus alpha. It is sine of omega c2 of n minus alpha minus sine of omega c1 of n minus alpha. Okay. This is the expression for hd of n. For what? For n not equal to alpha. Okay. This is the expression, okay, for hd of n. Therefore, it is given by sine times of omega c2 of n minus alpha minus sine times of omega c1 of n minus alpha, whole thing divided by pi times of n minus alpha, provided what n is not equal to alpha. Now, for the case, what? When n is equal to alpha, for the case n is equal to alpha, I must find what is hd of n. I'll just show you the equation and I'm substituting it directly. So what I'll do is, I'll just take back, considering this expression, I'll replace n by alpha. By replace what? N by alpha. Same thing, n by alpha. Then this term reduces to what? 1. 1 over here and 1 over here. So by using this equation, directly I'll write the result. Okay. So therefore, hd of n is given by 1 by 2 pi times. For the first means what? Integral of d omega is omega. What are the limits? Okay, it's omega minus omega c2 to minus omega c1. Therefore, by substituting the limits for the first integral, I end up as minus omega c1 plus omega c2. Similarly, for the second set, integral of d omega is omega, whose limits are plus omega c1 and plus omega c2. Accordingly, I get omega c2 minus omega c1. So therefore, the value of hd of n in this case turns out to be just plain omega c2 minus omega c1 divided by pi. Because a common factor 2, both in the numerator and denominator get cancelled. That is why the final expression for hd of n can be written as sine times of omega c2 times n minus alpha minus sine times of omega c1 of n minus alpha divided by pi times of n minus alpha, provided what? Provided n is not equal to alpha. Similarly, for the case when n is equal to alpha, hd of n is equal to what? Omega c2 minus omega c1 divided by pi, provided n is equal to alpha. So this is the solution for the first part of the problem. To continue further, what you can do is just what? Substitute the values. Substitute the values. Okay. In our case, what's the value of alpha? Alpha is what? Given by n minus 1 by 2. The value of n is given as 7. So 7 minus 1 by 2, 6 by 2 turns out to be 3. Therefore, substitute the value of alpha is equal to 3. Similarly, it's given that the value of omega c1 is 1 radians. Similarly, the value of omega c2 is equal to 2 radians. Then what? Substitute these values finally. Therefore, the final equation for hd of n would be equal to sine of the value of omega c2 is 2, right? Is 2 times of n minus alpha minus sine times of omega c1 is 1 times n minus, okay. Again here please substitute the value of alpha is what? 3, n minus 3 divided by pi times of n minus alpha. Pi times of n minus alpha is 3, provided what? N is not equal to alpha, which is equal to 3. For the case when n is equal to alpha, when n is equal to 3, it is omega c2 minus omega c1 by pi. 2 minus 1 is 1, or this what? 1 by pi for the case n equal to 3. This is the solution for the first part of the question asked in the problem. This is the answer. The next part is that they're given the windowing function for the Hamming window, and they've asked us how we can use the same function for the interval small n lying between 0 to 6. Now let's get on to the part B solution. Part B solution. Part B solution. What is given to us? It is given that the Hamming function, okay, the windowing Hamming function is given by 0.54 plus 0.46 times cosine value of, I just forgot the 2 pi n by n minus 1. Yeah, it's cosine value of 2 pi n divided by n minus 1. Please note that this value is equal to what? Minus of, and why is it valid? It's valid for minus of n minus 1 by 2 less than or equal to n less than or equal to plus n minus 1 by 2. And please note that here if you could substitute the value of n as 3, the above equation is what? Is valid for what? For the value minus 3 less than or equal to n less than or equal to plus 3. And what happens if you could draw the table for the value of n, the value of hd of n, and what is your, what is that? Hamming function, windowing function. This value, finally the value of h of n, finally the value of h of n. Okay, let's substitute the values. This is as per the range of n varying from -3 to +3. -3 to +3. What's the range of n? We start from where? We start from -3, -2, -1, 0, 1, 2, and 3, and 3. So if you could just what? Substitute these values in the windowing function, starting from n varying from -3 to +3. It is found that the values of the windowing function obtained would be 0.08, 0.31, 0.77. Then I think the value turns out to be 1, again 0.77, 0.31, and 0.08, 0.08. Okay, you can also substitute the values of ht of n and get the corresponding filter coefficient. You can fill it up for yourself. I will give you the windowing function value. But the point what to be observed here is from this from the above table, if you could observe this Hamming function for given window is said to be what? Is symmetric with respect to n is equal to 0, isn't it? At this point of time, n is equal to 0 is the mid value. With respect to this mid value, the windowing function was about symmetric because the value at +1 is equal to -1, the value at +2 is equal to -2, the value at +3 is equal to -3, is equal to what? -3. The values are symmetric with respect to interval n is equal to 0. And if you could observe the values of n, which is varying from -3 to +3, it shows that the given function is what? Non-causal in nature. Because for this, if you compute ht of n and compute h of n is said to be having values for what? Values of n less than 0. At n is equal to -1, -2, -3, the values are said to be existing. Since the values are existing for the values of n less than 0, it is said to be non-causal in nature. Now the question asked is, how do you use the same windowing function for what range? For the impulse response h of n, for the range what? For range n lying between 0 to 6. In the problem defined, the value of n is what? Varying from -3 to +3. So now the same windowing function should be okay modified such a way that I should be able to use it for given impulse response where the value of impulse response h of n is said to vary from n varying from 0 to 6. That is 0 less than or equal to n less than or equal to 6. For this particular range, I want to modify the windowing function. For that, for this thing to happen, that is what? That is to make, that is to make it causal, in nature. The word function is what? Non-causal. To make it causal in nature, what we must do? We have to shift. The window. We have to shift the window function. We have to shift the window function by the value of alpha equal to n minus 1 by 2 so that it is symmetric about what? So that it is symmetric about the alpha value, about alpha is equal to n minus 1 by 2. Alpha is equal to n minus 1 by 2. In this case, we could substitute the value of n as what? 7 minus 1 by 2. I end up at alpha is equal to 3. Instead of making it to be in the earlier case, what? In the earlier case, it was symmetric with respect to interval 0. Now, in the present case, to make it causal in nature, I'm shifting the whole of the windowing function by the value of alpha is equal to n minus 1 by 2. The intention is that I want to make the response symmetric about alpha is equal to n minus 1 by 2, which is equal to 3. Therefore, the Hamming windowing function is given by W Hamming of n minus alpha is equal to W Hamming of the given windowing function n. What were the values which we obtained? The table 0.08, 0.31, 0.77, then 1, and again the same values were repeating. What this 0.77, 0.31, and 0.08. But please note that since I've shifted it by a factor of 3, instead of omit now, I've shifted by a total of 3. Instead of minus 3, minus 2, minus 1, I must start the interval from 0. So whatever is the first sample I'm having it over here, this is for indexing n is equal to 0. This is for 0 sample, first sample, second sample, third sample, fourth sample, fifth, and the sixth sample. So please note that with respect to this value of alpha is equal to n minus 1 by 2, the new windowing function is symmetric. This is symmetric about the midpoint 3 means the value of 4 is equal to 3, the value of 5 is equal to 1, the value of 6 is equal to the value at n is equal to 0. Value at n is equal to 0. Now with respect to this new function, you can form a new table to find the filter coefficients h of n. To find the filter coefficients h of n. Where is this? Yeah. So this is n and this would be h d of n. This would be your windowing function w h a m of n. The last one would be h of n. H of n. Okay. I can't draw it, the straight lines. Okay, so please do adjust. Okay, concentrate on the calculation and the values. What is the range? It's not from minus 3 to plus 3, but the new range from what? 0 to 6, 0, 1, 2, 3, 2, 5, 6. Only about 7 values. Okay, I want to the values column wise. Do check the values once they're going to the recording. Just don't read the values, do check the values. We have done it correctly. Minus 0.265, 0.021, 0.318, 0.021, minus 0.265, minus 0.044. Note that is symmetric with respect to the mid value. Similarly, the windowing function values are 0.08, 0.31, 0.77, 1, 0.77, 0.31, 0.08. The corresponding filter coefficients value are minus 3.52 into 10 raised to minus 3. Next value is minus 0.08215, 0.01617, 0.318, 0.016, minus 0.08215. Okay, 16. Yeah, the same values has to repeat 1617 only. The last value is minus 3.52 into 10 raised to minus 3. Please note that now the new values, okay, of h of n makes the response to be what? Causal in nature. Because the h of n equals response is causal because the values are existing only for values n equal to 0 and greater than 0. For values of n less than 0, it is 0. So we have converted the non-causal nature, okay, into its cause and nature. Okay. This is the solution for the given problem. Kindly go through it, do the calculations once. If still there is any doubts, when you come back to the live class, you can get it clear. Okay. Thank you all.